I'm going to quickly go through the notes on sections 3.7 through 3.10. This is on solution formation and a little bit on chromatography. So we're going to look at mostly aqueous solutions. So remember, you're looking at a homogeneous mixture. The solute is what gets dissolved. The solvent does the dissolving. So the solute and solvent will interact if they have similar structures and polarities. Terms like soluble and insoluble. And for liquids, miscible and immiscible. Just terminology. So for the most part, we are looking at aqueous solutions, and water is a really good solvent for polar molecules because of its partial negative and partial positive end. So it's quite polar and can dissolve polar substances and even induce a polarity in small nonpolar molecules. When you're making a solution, you need to be able to describe the steps. So first you have to expand the solvent, which means break apart. So if you have an ionic solid, you have to break those ionic bonds and then break the solute. So if you have water, you have to separate the hydrogen bonds. And then you have to mix the solvent and solute. And this will depend on whether or not they can attract each other. So you expand the solute by adding energy. So if this was an ionic solid, you'd add energy and expand the solute and expand the solvent. And that's going to take a little bit of energy. So those are positive delta H. In terms of thermodynamic, those two processes are not thermodynamically favored. If the solution cannot form, so once you've expanded these, then you have to have some attractive forces between the solutes and the solvent in order to form your solution. So if you have that, that will be the driving force that allows for the solution to form. So if molecules can attract each other, the solution will form. If they cannot attract each other, if the polarities cannot be induced, so if water cannot induce a polarity in whatever this solute is, then the solution will not form. Don't ever just say like dissolves like, but that's really very truly what you're looking at when you look at those structures. If you have a non-polar substance, it will not dissolve in a polar solvent. If they are both polar, you'll get some solubility. If they're both nonpolar, you will get solubility. If your solute is a small molecule, then often water can induce a temporary polarity and hold on to it in something called an ion-induced dipole or an induced dipole. So step 3, the formation of the solution, depends on whether your molecules can attract each other. So if you're looking at something like ethanol, so here's your ethanol structure. It's got a large part of the molecule is nonpolar, but it does have this polar part, and this also has the ability to hydrogen bond, not only to itself, but also to water. So water can hydrogen bond with the hydrogen in the ethanol because the hydrogen molecule in the ethanol meets the criteria of hydrogen bonding. It is covalently bonded to NO or F. Therefore, the hydrogen here can hydrogen bond to the oxygen here. Just as easily, the hydrogen here could hydrogen bond to the oxygen here. So if you remember back on a test one time, you had to draw where the hydrogen bonds attached, and you had some issues with that. So we'll look at that in some of our free response. So hydration is another term that fits into this topic. You're talking about breaking down the ions of salts and then surrounding them with water molecules. So now you have an ion dipole attraction. So if you have an ionic compound, that has charged species, then you can get the negative part of water to interact with the positive ion and the positive part of water to attach to the negative ion. This is called ion dipole attraction, and it can they can ask you questions about the size of the ions. A smaller ion is going to be able to be hydrated more fully. A highly charged ion would attract the water molecules. So there's all kinds of structural things that can be asked about solutions. So your polar water molecules interact with the positive and negative ions and eventually surround the cation and anion in a process called hydration. If you ever have to draw this, make sure when you are drawing your water molecule that your positive hydrogens are attached to the negative ion and your negative oxygens are attracted to the positive. So when you're drawing a solid crystal lattice, you would draw this, but a soluble ionic compound, you would separate your ions 100%. So water-soluble molecules have dipole moments or polarities. Some nonpolar substances can dissolve slightly in polar solvents due to this dipole-induced dipole, or an ion-induced dipole, or a dipole-induced ion. Or there's lots of ways to explain how the dipole of water attaches itself to ions or to nonpolar molecules. Again, this is what you're looking at, but you're never writing this. So if you looked at this trend, you have all these alcohols, okay? And they have this polar group that can definitely hydrogen bond, but as your group becomes a more significant part of your molecule, or the nonpolar part of your molecule becomes larger, you can see the solubility decreases. So when you have a polar group, then you do have the possibility of water hydrogen bonding in this area with the OH group. But once your nonpolar portion of your molecule becomes so large, then you really can get very little solubility. Notice there's still a little bit because you are getting a dipole-induced dipole, but it's much, much less soluble. So you could be looking at a structure and looking at the part of the molecule that is nonpolar becoming significantly large, and you're having a difficult time inducing a polarity there. So if you were drawing your hydrogen bond between things that can hydrogen bond with each other, so here's methanol attaching to itself, so the hydrogen on one methanol attaches to the oxygen of the other, and then here's methanol hydrogen bonding with water. Again, the hydrogen on one attaches to the oxygen of the other. What you don't want to think is that this hydrogen can attach and make a hydrogen bond. That's not true. This hydrogen cannot hydrogen bond. It is not bonded to NO or F. And that was some of the mistake you made on your test a long time ago, if you can remember that. Ammonia also has the ability to hydrogen bond to itself and to water. Okay? So these hydrogens could hydrogen bond to the oxygen because they are covalently bonded to NO or F. This hydrogen can attach to this nitrogen because this hydrogen can hydrogen bond. When you have induced dipoles, you're looking at fairly small molecules like oxygen or CO2 or nitrogen, where water's strong polarity can induce a temporary polarity in the oxygen molecule enough to hold on to it. Sort of similar when you think of your London dispersion forces, but these are two different species. But you do get a slight difference in charge, so you might get a negative and positive end on that molecule, and then the water can attach itself to its negative positive end. So we know that oxygen dissolves in water to a small extent, and that is how it does it. So the dipole of water induces a dipole in oxygen by distorting the electron cloud. And then you have this attractive force between this positive end and that negative end. So you get a dipole-induced dipole. That's the term you want to use when you're talking about nonpolar substances being able to be dissolved in water. A dipole-induced dipole. So I did this demonstration for you where I had 3 different solvents, and this one is water. So if that's water and water's polar and these don't mix, then you know that they're both nonpolar. We then introduced some nonpolar iodine. Remember, iodine I2 would be a linear nonpolar molecule, so you would expect it to dissolve in these 2 layers, which it will. Will not dissolve to any degree in the polar layer. But if you notice, here the water layer is quite clear, and here it's got a little discoloration. So there is some dipole-induced dipole. The water's inducing a little bit of polarity in the iodine and will dissolve it a little bit. Then if we mix these together, all 3 of them, and let them settle out, we now can tell that the 2 nonpolar, along with the iodine, dissolved, leaving the water behind. And the fact that this floated on the top just meant that the combined density was less than the water's density. So electrolytes are parts of solutions that you need to know. So electricity is moving charges. When we're talking about our metal bonding, we're actually talking about electrons moving, but now we're talking about ions that dissociate and move. So you have soluble ionic compounds that can conduct electricity, and we call these electrolytes. So ionic compounds that are dissolved, solutions of ionic compounds, are electrolytes. You have 3 ways that you can classify these electrolyte solutions. Strong electrolytes dissociate 100%. So if you stuck a conducting light bulb in there and allowed the electrodes, you would have 100% ions, so a drawing would show 100%. The light bulb would be bright. Many ions would be a strong electrolyte. A weak electrolyte would only partially dissociate, less than 1 or 2%. The light bulb would be dimmer, and while you would have some ions, you would have mostly non-conducting molecules, so a slight conductance. And then you have non-electrolyte substances that do not dissociate. They may dissolve, but they don't dissociate. Remember, dissociation is for ionic compounds only. Dissociate means to form ions. So if you have no ions, you have no conductance. Even if you're soluble, even if you dissolve 100%, you're not going to be an electrolyte. So your types of solutions: strong electrolytes contain many ions and conduct well. Weak electrolytes, few ions. And non-electrolytes, no ions. The solutions that give you these types of electrolytes are as follows. Strong acids and bases are written as ions when you write them in solution. So we haven't reviewed net ionic equations yet, but when you have a strong electrolyte, you must write it as ions. You are showing that it's 100% ionized. So soluble salts are strong electrolytes when they're in solution. Weak electrolytes would be your weak acids and bases. So your soluble salts and your strong acids and any hydroxide base, okay, would be soluble. So you've memorized your strong acids by now. Any hydroxide base and all soluble salts are strong electrolytes. Your weak acids and weak bases are less than 1% ionized, and you write those in your net ionic equations as molecules. And then your non-electrolytes are insoluble salts like silver chloride. You do not ionize. Silver chloride's a precipitate. And any molecular compounds like water, you don't write an ionization of water. Now, of course you do when you're thinking about the equilibrium of water, but when you're writing water as just interacting with another species, you think of it as a molecular compound. So only when you get to your advanced acid-base chemistry do you think about ionizing water. So HCl, you've memorized it as a strong acid. You would represent it as all ions. Acetic acid, if you were to draw it, you would represent it as molecules with a few ions. You might put a couple of ions in there, but mostly molecules. Very few H plus ions. That's how your particle diagram can differentiate. So your structure of your acids and bases that control why they're strong or weak is, you know that if you have an H in a molecule, that it's a potential acid. And that acid molecule, that acid H, is attached to an oxygen. The stronger your H bond is, okay, so you're often looking at a hydrogen attached to an oxygen in an organic acid, but often you have things like HF and HCl, your simple binary acids, and of course your hydrogen is either going to be attracted strongly or not as strongly. So a weak acid has a strong bond, and a strong acid has a weak bond. The more polar the bond, the more acidic, because the stronger acid you have. When you're looking at oxyacids, these are the ones where your hydrogens are bound to oxygens. Your hydrogen is bonded to an oxygen. The oxygen is very electronegative, pulls electrons away from the hydrogen. So the more oxygens you have, the stronger you have that electronegativity pulling these electrons away and weakening that bond. Molarity in solutions, you just have to be able to calculate all molarity. From molarity, get moles, get grams, get liters that you need. So the definition is moles per liter of solution, moles of solute per liters of solution. Again, make sure you write a big M. Some of you get into the habit of writing those lowercase m's that are not going to work for molarity. So a stock solution is one that's already been prepared and standardized. That's a terminology you need. Concentrated means you've got a large amount of solute, and dilute means you have a very small amount of solute. So stock, concentrated, and dilute. To make a solution in a volumetric, usually it doesn't show it here, but if it's a solid, usually put a little bit of water, dump your solid in, swirl it around, and then rinse the sides down, shake it fully, and then fill to the line. So often they will ask you the steps for making a solution. You can use a better measuring device when you make a solution by using a pipette rather than a graduated cylinder. When you have a solution that's already made and you want to dilute it, you definitely want to use this M1V1, M2V2. But always make sure you at least put some labeling down there because it's the molarity and volume of your first solution is equal to the molarity and volume of your second. MV equals MV, they very well may not give you credit because you might luck into putting the correct things together. So when you add more solvent to a known solution, the moles of the solute will stay the same. You're not changing the moles. you're just diluting it. And moles always equals molarity times volume. Moles always equals molarity times volume. That's extremely important in any of your calculations doing with solutions. So M1V1 equals M2V2. The moles are not changing. So this is an equality statement. So you can solve for any of those missing parts. Chromatography is the last topic that I'm going to discuss in these sections. So you're looking at like dissolves like, even though you're not going to say that. You're looking at the ability to separate molecules based on their structure and polarity. So it's a method of separation, physical separation, no chemical reaction, by having two or more compounds distributed between two phases. One phase is stationary and the other is mobile. So one phase moves and the other stays still, and your molecules have to be attracted to both to varying degrees. So the method depends on different structures, and that depends on the structures of your stationary and mobile phase. So if a substance is more attracted to the mobile phase, then it's going to travel faster up the chromatography paper than a substance that's more attracted to the stationary phase. But if they were attracted to only one phase, they either wouldn't move or they would simply move and dissolve into that phase. So structure and polarity. So we did the column chromatography, which is the stationary phase is in the column, and then you pass the mobile phase through, and you were able, some of you successfully, to separate out the red and blue dye in the grape Kool-Aid. We did not do a paper chromatography because you should have done that. Well, I know all of you that had me, and I know Ms. Novak as well, did the fluorescent dye paper chromatography. So I doubt they would ever ask you this, because many students don't have access to those. So let's review your chromatography in general and then your paper. So it really doesn't matter if you are passing things through a column or moving them up a column. The idea is still the same. You put your mixture, and based on the attraction, and you would put your mobile phase in, and it would pass through, and it would then attract molecules of similar polarities. So separating a dye mixture is really, in my opinion, first year chemistry. You should have done it in biology, but it's certainly the one they're most likely going to ask you. So your stationary phase is the paper, and your mobile phase is the solvent. And you can see that you have several substances here. You almost typically always have a known, and then you compare it to the unknown to see. Now, not all chromatography has color in it. It did originally, chroma, but you can use ultraviolet lights and so on. But what you're looking at is to see if your substances have risen to the same height compared from where they started to the solvent front. So you spot your plate or piece of paper with a very tiny amount of either the pure dye or the mixture, and then you stick it in a chamber and you develop it. Once you're done, you draw the solvent front as quickly as you can before it dries, because you want to measure how far the solvent front travels compared to how far your dots traveled. Now this was an experiment we would have done towards the end of the year with a UV light using caffeine and separating caffeine. So you really would need an ultraviolet light to visualize the caffeine here. But for most substances, you will have a color. You will measure the height of the dot over the height of the solvent front. So I know that in one of the AP review videos, they had a chromatography question. We'll certainly go over one. Theirs was interesting because they had two different plates. Normally, you put all of your substances on one so that you don't have any difference. But what you're trying to calculate is what's called the retention factor. So how much is retained on the paper and to what height. So it's pretty clear here that none of these are the same substance. But let's say we had a substance right about here, then these two appear to be the same based on their retention factor. The distance that the spot travels over the distance that the solvent front. So we'll do some chromatography questions that might show up on the exam. So this is the end of solutions and solubility.